Hello everyone. I am sorry that I had to be gone today, but the soccer team is playing Missoula Big Sky in Missoula, so that's where I am at. Since we just took our Chapter 1 test today, we will be starting Chapter 2. So if you haven't, make sure that you grabbed a new assignment sheet and note packet as you came in. They're over by the door where they usually are. So if we need to, pause the video now until everyone has their note packet and assignment sheet, and then the note packet out and ready to go, because we are going to be starting Chapter 2, Section 1. So we're going to be doing 2.1, Writing and Graphing Inequalities. So pause the video now until everyone's ready to go. Then you can press play once everyone's set. Okay, welcome back. Since everyone's should be ready to go, now we're going to start with a little warm-up question, a little ACT prep, just practice with some older skills, more like pre-algebra skills, but actually the ACT has about 20 to 25% of the questions are on pre-algebra skills. So we're going to review them every now and then, just get used to them. So the question is, what is the greatest common factor of 42, 126, and 210? I'll let you try here in a second, so I'll ask for our guest teacher to pause the video. But it asks what's the greatest common factor. Well, first you need to recall what a factor is. Factors of the number 12 are numbers that divide evenly into 12, like 1, 2, 3, 4, 6, and 12. Those are all factors of 12. So what we're looking for is we're looking for the biggest number that will go into 42, 126, and 210. They give you some options over here. So pause the video now, give everyone a chance to try this. You could probably try just at the top of your note packet to jot it down. So pause the video now for maybe a minute, give everyone a chance to try, and then we'll come back. We'll talk about some strategies for solving a question like this that might be on the ACT. Okay, welcome back. If I were to get asked this and I were a student taking the ACT, if they give you options, use those options to your advantage. Start with the biggest number and see if it divides these three numbers, and if it's the biggest one and it does, well, then we have our greatest common factor. It goes into all of them, making them common, and it'll be the biggest one. So let's check 42. Does 42 go into 42? Yes, it goes into 42 once. Does 42 go into 126? Well, check. On your calculator, type in 126 divided by 42, and when you do so, you'll find that it actually goes in there 3 times. So it's a common factor of 42 and 126. Now check to see if 210 is divisible by 42, and it actually is. 210 divided by 42 is actually the number 5. So because 42 divides all of these, it's a common factor, and it's the biggest one in our list, so it's going to be the greatest common factor. So we're done. It's actually J. So there's the quickest way to do it. Another way to do it is to actually solve it mathematically if you didn't have a list, and the way that you found greatest common factors was you made factor trees. So just a little aside on how you could do that. You start with 42 and you break it down into its factor tree. It's divisible by 2 times 21. And then 2 can't be broken down anymore, so I write 21 as 3 times 7. So 42 is 2 times 3 times 7. Now, let's try 126. 126 is going to be 2 times 63. 63 is 3 then times 21. And 21 is 3 times 7. So 126 is 2 times 3 times 3 times 7. And then I look and see what do they have in common. They have a 2 in common. They have a 3 in common. They don't have another 3, but they have a 7 in common. So the greatest common factor of 42 and 126 is 2 times 3 times 7, and that's actually 42. If I did a similar tree for 210, I would find again it has a 2 times a 3 times a 7 in it. So that would be the greatest common factor of all 3 numbers. That's the long way to do it, so I don't recommend doing that. If they give you options and it's a multiple choice question, use those options to your advantage. So that's just a little ACT prep, test taking strategy, and a little pre-algebra review. Your notes will actually start with the next slide. So have your notes out and ready. What we're going to be studying in this chapter, we studied last chapter how to solve equations when something exactly equals something else, but now we're going to study what are called inequalities. Although we've been studying equations where something was exactly equal to something else, that doesn't happen all the time. Rather, sometimes something is bigger or smaller than something else. Some examples. The speed limit says on the interstate that we must drive less than or equal to 80 miles per hour, 80, as of about 2 years ago. It used to be 75. When taking a suitcase on a plane, it must weigh less than or equal to 50 pounds. It's another inequality. It's not. It doesn't say it has to exactly weigh 50. It says you can weigh 50 or less. What does this sign imply right here? This sign says in order to ride the carousel, the minimum height for this ride is 130 centimeters. So what does it say? It says the height has to be, height is greater than or equal to 130 centimeters. So those are some examples of inequalities in real life where things don't have to be exactly equal to. They can be equal or bigger, or equal or less, or maybe just less, or just bigger. Those are all examples of inequalities. We use a variety of symbols to denote inequalities. An inequality, this might be a vocab term, so look at your note packet. An inequality is a mathematical sentence that compares expressions using the signs left arrow, less than or equal to, right arrow, greater than or equal to. No one actually says left arrow or right arrow. If it points to the left, that is less than. And the reason why arrow pointing to the left is less than is because on your number line, numbers, like let's say if this is 7, numbers to the left of 7 are smaller, like 6 or 5 or 4. So numbers to the left of 7 are less than. So left pointing arrow, less than, or people might say fewer than, or up to. If it has a bar underneath, it means it's part equal. That means it could be less than or equal to. Or another way of saying that is no more or at most. If it's an arrow pointing to the right, that means greater than, and the reason why has nothing to do with alligators and all that you might have heard before in middle school or elementary. It's because an arrow pointing to the right on my number line includes my numbers that are bigger, like 8 or 9 or 10. Those are all numbers that are bigger. So pointing to the right, greater than, more than, exceeds, in excess of. If it has a bar underneath, it's like a combination of equal to and greater than. We say it's greater than or equal to. Some examples. What we're going to do is we're going to take all of those things that we just said 2 seconds ago in English sentence. We're going to convert those to an inequality. So first one, speed limit says on the interstate we must drive 80 miles per hour or less. So our speed has to be less than or equal to 80. That's an inequality. When taking a suitcase on a plane, it must weigh 50 pounds or less. It can weigh. So weight can equal 50 or be less. So we say weight less than or equal to 50. When riding the carousel, you must be taller than or equal to 130 centimeters. So your height must be greater than or equal to 130. Last one that you might care about more when you actually are over 18 and start working. To earn insurance benefits, you must work more than 19 hours per week. So hours, could use H again, have to be greater than 19. It says you have to be greater, not equal to 19, you need to be bigger. So 20 or 21. These are all examples of using mathematical notation to write a big sentence. Look how much words I just would have had to say. Look at that. That's a long sentence. And I just described that mathematically with an S, a less than or equal to, and an 80. So it's much more efficient. And in math, we're all about efficiency. So we're just translating from English to math. We're translating inequalities in a very efficient manner. So those are just some examples. What I would like you to try on the whiteboards are the following. I would like you to try on the whiteboards, try to translate these guys. Something like 15 is more than or equal to a number t divided by 5. The second one is 3 is less than the sum of a number x and 7. And in this case, just so I can see how you might get confused, we're talking about inequalities. So this less than isn't going to be subtract. It's going to be actually our less than sign. So don't get confused about that one. The more than I think you should be okay on. So maybe pause the video now, pull out the whiteboards, Try translating these two English sentences, statements, into mathematical sentences or inequalities. Pause the video now, give everyone maybe a minute to try these two. We'll come back and see how you did. Okay, welcome back. Let's try the first one. First one translated, it says, let's go a little piece by piece. It says 15 is more than. So 15 is more than, so is greater than. It says or equal to a number t divided by 5. So I'm going to take t and divide it by 5. There we go. I've just translated that English sentence into a mathematical inequality. Second one says 3 is less than the sum. Sum means addition, so it's going to be less than the addition of a number x and 7. So I'm going to be 3 is less than x plus 7. There we go. And I've translated those two. Hopefully you did okay on that because you'll be asked to do that on the homework today. So now we can translate. Next part we're going to do is after translating, we're actually going to graph these guys. Just like I graph them on the number line, I can translate and graph them even if they're real world scenarios on a number line. So instead of writing this statement mathematically, we can also use a graph to communicate what we're meaning. Example, the speed limit says on the interstate we must drive 80 miles per hour or less. So on my number line, I would have maybe here, I'm going to label it S for speed, and I have 80 here. I'm going to do some tick marks. Okay, maybe I've got 81, and then 82, and then 83, and I think you get the idea. And then to the left, I'd have 79, 78, 77. Now it says, speed limit says on the interstate I must drive 80 miles per hour or less. The way I graphically show that, I put a circle around 80, and I shade to the left because it's less than. Any of these speeds, I would not get a speeding ticket. Because I can drive 80 miles per hour, it's equal to 80 or less. Our speed is less than or equal to 80. The way that we say you can drive 80 is we fill in the circle around 80, saying that you are allowed to drive 80. That would be how we could graphically demonstrate that English statement. Let's try the other one. The other one was insurance benefits. It says, to earn insurance benefits, that means your employer will help pay for like medical costs if you need to go to the orthodontist or the dentist or you get sick. They'll help pay for part of those. You must work more than 19 hours per week. So hours is my variable, so let's label my number line H. That's what I'm counting. The point of interest is 19, so let's put 19 in the middle, and then above it we got 20, 21, and 22. Below it, I've got things like 18 and 17 and 16. It says I need to earn or I need to work more than 19 hours. So I'm going to put my circle around 19. That's my point of interest. I need to work greater than 19 hours. So I'm going to shade to the right. If I translated, it would have been hours needs to be greater than 19. Can I work 19 and earn the benefits? No. It says nothing about equaling 19. I need to work 19 hours. I need to work more than 19. If I work 19 hours, I will not have earned it. I need to work actually bigger than 19. So it's an example of graphing an inequality, even in a real-world scenario. Okay. We're going to fill in this table just so you have a reference sheet while you're doing the homework. So we're going to fill in the blanks to complete the table. If I look at this graph here, can we go backwards? So I gave you the verbal description 2 seconds ago, and then we graphed it. Now we're going to do the backwards. If you have the graph, can we translate to algebra and then back into words? So we're kind of making sure that we're good translators. We're translating it forwards and backwards. So let's look at this one right here. This says I need to be less than 2. I cannot be equal to 2. I need to be strictly less than 2 in this first one. So I'm going to put just a left pointing arrow. I want everything to the left of 2. So x is less than 2. Now, in this second one, I want everything above 2, everything to the right of 2, everything greater than 2. If I want everything greater than 2, I put a right arrow. It doesn't include 2, so I don't put an equals bar underneath, half an equal bar. So this is strictly x is greater than 2. Greater than 2. Let's try the third one. Third one says I need to be the left of 2, or I can actually be equal to, and I know that because I see this is filled in right here. That's a key thing to note. That's a big point. Because it's filled in, I can be equal to 2. So I want to be less than or equal to 2. So x is less than or equal to 2. Final one that we could have is we want all the points above 2 or on 2. So x has to be greater than or equal to 2. I put a bar underneath. X is greater than or equal to 2. There's our reference sheet. So now you should be able to graph anything. Less than, greater than, less than or equal to, greater than or equal to. Last part that we're going to talk about is then checking solutions, whether a number makes an inequality true or false, just like we were talking about with equations. So similar to equations, we can check to see if certain numbers are solutions to an inequality. What does it mean to be a solution? It means that you are a number that makes an inequality true. It reads correctly. It makes logical sense. Yeah, that might be one of your vocab words. So look to see if solution of an inequality is one of your vocab words. You'll need to fill it in your note packet. A number that makes an inequality true. And there is a key difference. For equations that we've studied, there was only one number that made the equation true. Something like x equaled 3, x equaled -5, x equaled 10. There was only one number that made it true. For inequalities, there's going to be lots of numbers that make it true. We call it a solution set. Like for example, if I asked you what is the solution of the speed limit situation, you could say 79 or 78 or 77. As long as it was less than or equal to 80, then you would be true. Those would all be solutions. So there is a key difference between inequalities and equations. Equations only had one number that made them true. Inequalities will have a bunch of numbers that make them true. There's a one solution set though. That's the similarity and difference. So example though of checking whether a number makes an inequality true. First one says, tell whether -4 is a solution of the following inequalities. So I'm going to take -4, I'm going to substitute it in for x. -4 plus 8 less than -3. Let's check. -4 plus 8 is 4. Is 4 less than -3? No, 4 is not less than. 4 is not to the left of -3. Say no. So I'd say -4 is not a solution. It did not make a true statement. 4 is not to the left of -3. It is not less than. Let's try it over here. Let's put -4 in for x right there. So I've got -5 times -4 is greater than or equal to 20. -5 times -4 is 20. And then I need to ask myself, is 20 greater than or equal to? And there's a key part. There's the word or. When there's the word or used, you would just need to be one or the other. We call that the union. That you don't really need to know right now. You just need to know it needs to be one or the other for an or. 20 is not greater than 20, but it is equal to. And so this is true. 20 is greater than or equal to 20. So this is a true statement. So -4 is a solution. Right? Moving along. Your job is to check the following. You tell me, is 6 a solution of the following inequalities? If you substitute 6 into each of these, does it make them true? If it does, it is a solution. If it does not, it is not a solution. So pause the video now. Give everyone maybe a minute and a half to try this on the whiteboards. You can check with your neighbor, see if your neighbor agrees, yes or no for both of them. Then once everyone's had a chance to try, unpause the video, resume. We'll go over it and make sure that you're on the right path. Okay, welcome back. Let's check this real quick. When I substitute in 6 for x, in the first one I get 6 plus 8. Is that less than 10? 14. Is 14 less than 10? No, it is not. Not true. 6 is not a solution to the first one. False statement. Let's put 6 in over here. 6 divided by 3, is that greater than or equal to 0? Yeah, I get 2. Is 2 greater than or equal to 0? It's not equal to, but it is greater than. And as long as it's one or the other in the or statement, it is true. So this is true. So we would say 6 is a solution to this one. It worked for the first. It did not work for the second. That's it. All you're doing today is translating inequalities. So your homework is actually on the assignment sheet. It's day 1. So look at your assignment sheets. It'll be some questions in the book for you. If you have any questions, this video is recorded and saved on my website. You can go on the website at your own convenience and go over it if you need to. Otherwise, have a great rest of your day, and I'll see you soon. Thanks.